Hello MCP users, and welcome to the second session of Micro CT training. Today we're going to take a look at CT reconstruction, where we'll take the set of projection images that you acquired on the instrument and transform them into a set of XY slices, which we'll use to do further processing later on down the road. CT reconstruction can be rather computationally intensive, so we have a dedicated PC to do this job. It sits to the left of the acquisition PC in the Micro CT lab. First, we're going to open Exact64. This is the same software that's used on the acquisition PC, but you'll notice when you load the software that an entirely different set of plugins is assigned to this software. So we see first that we have a set of drop-down menus, a set of frequently used tools along the top, as well as this UniCT plugin on the right panel here. Initially, there's not going to be very much going on in the software because we haven't loaded any data yet. So that will, of course, be the first step. So we have the Load tab available in UniCT here. And so the first thing that we'll do is choose our reconstruction project. So to do that, we click the folder icon, and we are able now to choose which project we want to load. Where your data is located is going to depend on where you chose to save it on the acquisition PC. So for the sake of this training, I'm going to use a data set that I've already processed before. So you'll find that you have a proj folder. This folder contains all of the raw images, a proj-ref, which contains the reference images, a report folder, which contains little, sometimes useful bits of metadata, and then once you actually run the project, you generate a slices-y folder. And so you can tell that this project has already been processed because I already have this slices-y. But to open a reconstruction project for the first time, what we're going to do is select this Uni Reconstruction XML file. So we can double click on this, and we can see that Exact64 will start to load the images that are contained in that project. As it loads, we can see the images populating this folder. If we grab the slider bar that can be seen on the bottom here, we can scroll through the entire set of projection images to make sure that they're all properly organized and they're all looking as we expect. We can also see a familiar histogram at the bottom of the screen here with the same controls as it has in the acquisition software, where you can drag to stretch and compress the range, or you can flip to a negative image if so desired. If I press Control and use the mouse wheel, I can zoom in and out. When I do that, we can see this box with 3 sets of axes and also 2 circles. This box represents the entire volume of the sample that we've analyzed. And the green, red, and dark blue squares represent which test slice we are using. This will become more important later on, but for now you can just note that it's possible to drag each of these axes wherever we want them to be within the total volume of our object. Also in the Load tab, we can see a few other controls that we have. Under Settings, we can choose to load all projections if we're going to do a final reconstruction, or we can choose a subset of projection images. So say we were to choose 25%, it would only load 1 out of every 4 images that we acquired, but it would be much faster to actually run the processing and reconstruction. This can be useful if you're only intending to try out certain corrections or try out certain data processing, and then go back and load all projections later on. We also see automatic geometry correction, automatic spot correction, and automatic reconstruction. I usually don't choose to use these because it only takes a few moments to do any of these corrections yourself, but if you have a simple sample that you're sure will be successful with an automatic correction, feel free to check automatic geometry and spot corrections. And if you want it to spit out a reconstructed data set automatically when you start loading a sample, you can choose to either reconstruct X slices, Y slices, or Z slices, or the volume. Now that we've got our data loaded, I'll start working through a typical CT reconstruction. Our tabs in UniCT now are load, volume, spot, geometry, filter, and so forth. And the software is organized such that you can usually move left to right along these tabs and finish up in the Reconstruction tab. So, the next step after our data set is loaded will be going over to the Volume tab. In the Volume tab, we have information about the voxel size as well as the size of the total volume, which is just the voxel size multiplied by the number of voxels. Here you can see numerically which slices the test slice is located, and that is these green slices, so we can see it change like so. Next, we're going to start correcting some of the artifacts that come from the CT acquisition. The first one is the spot correction. When we move to the Spot tab, we see a couple of graphs of offset, so here we have horizontal, here we have vertical offset, by projection index. This is why we took the reference images at each of these indices. The first thing to do to apply a spot correction is to start automatic correlation. Plus or minus 8 pixels is a good range to start with for this correction, but as we'll see in a moment, sometimes that might need to change. Here we can see once the automatic correlation completes, this line, which initially had been straight down the center, is starting to wave a little bit. What this means is that each of these references, there's a different offset value assigned. How we can visualize that is by showing differences with the reference images. Let's do this for example. Show differences with reference images. What appears may look uninteresting, but what we're actually seeing is a mask of the reference image over the actual image at that index. If we don't see anything, that means that the correction did a good job. A way to illustrate this is by selecting the dot that represents the reference that we're looking at right now and dragging it side to side. So here we can see the actual effects of the X offset. If the automatic correction was successful, this dot will be at the point where there's the least difference between the reference and the true image. The spot correction is very useful because it will compensate for any movement of the sample relative to the detector over time of your acquisition. So generally, you'll run it for each of your CT acquisitions. Usually the automatic correlation will be successful at finding the correct offset value, but say for instance your offset is greater than 8 pixels. In this case, you can increase the tolerance to 16, 64, or 256 pixels in order to find the correct correlation more successfully. If you ever are manually changing some of the correlation values, you can always fix it or get back to the original by Start Automatic Correlation. The computer will run the algorithm again, and it will bring it back down. Sometimes this requires an iteration before it will actually reach the correct value. And if we right-click on the graph, we can set all points to 0. Once we finish the spot correction, we'll move on to the next tab, Geometry. Probably the most important artifact correction that you'll need to run in this entire process is called Offset X. So that is, by default, the correction that's loaded in this Geometry tab. Since we have a stack acquisition for this data set, the software automatically knows to use Offset X stack /helicoil, but we can also see the standard Offset X. The only difference is that this will allow us to assign 3 different offset x values for different points along our sample. We can see that by clicking Show Table. And over here we have the table of all of our x offset values. Since we had 3 stacks in this acquisition, we have 3 different x offsets that we can assign. For now, they're all set to 0 because we have not done the correction yet. A good first step is to take a z-slice or y-slice in order to visualize what the correction needs to do. And so when I do this, it's going to just reconstruct one slice instead of the entire volume in order to save time. So we can see in this slice that we've generated a double edge. Now this doesn't look like it's the actual realistic sample, it looks like an artifact. In fact, this is the offset x artifact that we're correcting for now. We're going to let the computer run an automatic correction for this artifact as well. To do that, we move up here to the test box, make sure that offset x is the chosen correction, and click Test Geometry. This number of slices is the number of different test slices that it's going to reconstruct with different correction values, which we will see in just a moment. And so we can see here it's removed the double edge, but it's still not quite in focus, which we can see if we zoom in. What we need to do now is to actually increase the tolerance. So we're only looking in a range of 5 pixels to find the offset value. And it looks like we hadn't quite reached the proper offset, which we can see if we scroll through the different tests. So what we'll do now is increase this tolerance to 10, and then test the geometry again. With an offset of 10, we can see that our image is much clearer. And we can also see that our chosen slice is at the highest point of this curve. That's how we know we are at the correct offset value. When you've reached your desired x offset, you can move down to Automatic Offset X Correction and Start Correction. This is going to apply that to all of the slices as opposed to just the 21 test slices. This step will generally take several minutes to complete. Once the offset x correction is complete, we'll see up here that our offset x values have been populated for each of the stack IDs. Usually, at this point of a reconstruction, you'll notice a lot of tabs have been multiplying up here. That's because Exact64 keeps a history of each of the steps that you've done, all the way back to loading the projections. But we obviously do not need these images anymore, so every once in a while it's a good idea to delete some of these just to preserve computing resources. You may have noticed in the Geometry tab that there's several other geometry corrections that are available. Generally, these are not as critical as the offset x, but this can be something that you would experiment with if you have an unknown artifact in your dataset. Next, we'll move on to the Filter tab. The first option in the Filter tab is the ring filter, which is usually the most important. It's generally applied by default when you reconstruct a sample. Here we can see that it's selected and that it's set to 10 pixels. This value represents the radius of the rings that are going to be removed. Usually 10 pixels is a good place to start. If you're unsure whether you have ring artifacts or not, try out using a ring filter. Sometimes it will help, sometimes it will actually make the image worse. And it can be tough to predict. Below the ring filter, we have bad pixel correction and a bad pixel selection box. What these are for removing pixels in the detectors that we know are physically flawed. So They don't have a saturated or black pixel in each of our images. Fortunately, our detectors are quite new and don't have any faulty pixels yet. Next up, we have the Beam tab, which includes the Beam Hardening Wizard. Beam hardening is where X-rays are selectively absorbed on the outside of a sample before they even reach the inside of the sample. What that looks like is a gradient from light to dark, but it's within the same material system, so you know that it's an artifact. Usually this occurs when you have a highly dense material surrounded by a less dense material. It's not evident in the sample that I have loaded here, but if you suspect that you have beam hardening, please ask one of the CT managers. And we can instruct you whether it's beam hardening, and if it is, how to use this wizard to correct it. After the beam hardening tab, we have the advanced tab, which includes metal artifact correction and a phase contrast correction. These corrections are a little bit more sophisticated, and I won't describe them in detail here, but if you're curious or would like to know more, please ask one of the instrument managers. After the Advanced tab, we'll come to the Projections tab. This is where we choose which projection images are going to be used in the final reconstruction. Sometimes it can be useful to exclude a few projections, such as ones at the beginning or at the end of the sample, or if they don't contain any useful information, to save time. Or we can choose to use only a subset of projections, say every other projection. So here we have a list of all of the projection images, and to the left they have checkboxes describing whether they will be used or not. If we change this step value to 2, for instance, it will only use every other, or if it's 3, it will only use every third projection. This will increase the noise in our final image, or in our final 3D volume, but it will greatly reduce the amount of time it takes to reconstruct that volume. So, if you want a quick and easy reconstruction, just to see if your data is sufficient, it might be useful to increase this step number. But if you want the best possible reconstruction, you want to use all of the images that you acquired, and so you would use a step of 1. Additionally, you could apply a limited angle correction. This can be useful if, for instance, 90 degrees of your sample is obscured by a dense material, and you need to exclude that proportion of the projections. Finally, that will bring us to the Reconstruction tab. You won't ever need to change filtered back projection, and you won't usually need to adjust the noise or border filters, but contrast can be a useful tool. When custom contrast is selected, it will only save the grayscale values that are visible in the image as you see it now. If custom contrast is deselected, it will save the entire histogram. For instance, if I wanted to only save this visualization, I could adjust this histogram, select custom contrast, and choose contrast value from image, and a reconstruction containing only these grayscale values would be saved. I generally recommend not using custom contrast because you will be saving the entire histogram, and you can adjust the contrast and brightness later on in other software packages. Beneath custom contrast, we have the save box. Here's where we can select what we would like to output our data as. We have X, Y, and Z. This represents saving a stack of Y slices, X slices, or Z slices. Which one is most useful for you will depend on your sample. We also can select which data type to save as, 16, 8-bit TIFFs, or JPEGs. And we can choose whether or not to save a video. This video option will simply give us a fly-through of all of the slices of that axis. And if if we want, we can export the file as an STL as well. At this point, once all of our corrections have been applied, our contrast adjusted, and we are saving the data that we want to save, we simply need to click Volume Reconstruction. Since I've already run this once, it will ask if I'd like to overwrite it or create a new folder. I'll create a new one just for this, and just mark it as number 2. It asks if we want to close all images for improved performance, generally yes, and it will start to reconstruct. Depending on the size of your data set, this could take anywhere from a few minutes to several hours. Once a reconstruction is complete, you will see 4 quadrants pop up. These include the X slices, Y slices, Z slices, as well as the STL surface rendering. The yellow lines in each of the slices represent the surface calculated by the software and what is used to create the surface rendering in the bottom right. The surface rendering can take quite a bit of time to load, and so if you would like to accelerate visualizing your images, you can turn the surface rendering off in the menu bar at the top here. The contrast level which defines the surface is automatically assigned by the software, but it can be adjusted in the histogram. You see this orange bar can be dragged left or right, which will adjust the surface to any level of contrast that you desire. Although note that the more complex the surface is assigned, the longer it will take to render. The yellow markers can also be distracting, and they can be turned off in this menu item. It can be very useful to scroll through the axes in each dimension. That's what the colored lines in each of these quadrants are for. If you drag across, you will see the images in the other quadrants scrolling through slices. Likewise, you can do this in each dimension. This can help you pinpoint a certain location in your sample. For instance, if we wanted to look at this small crystal inclusion, we can drag our cursor to line up on that point, and then in each of the quadrants we will see the same object from different directions. If only one representation is of interest to you, the layout of this screen can be changed at the menu bar at top. If you only would like to see Z slices, that can be selected. In this view, the slices can be scrolled through using the mouse wheel. At this stage, you will usually want to take your set of XY slices and import it into another software such as ORS Dragonfly or Aviso in order to do further filtering, thresholding, segmentation, and other processing operations. It is possible to do some rudimentary measurements within Exact64. Measurement tools can be found along the top menu bar. Here we have line drawing, sphere drawing, as well as other shapes. To measure, we can choose length and measure by clicking once to set a start point and clicking again to set a stop point. Here we have our measurement. The measurement can be deleted by using the delete point tool. Note that both ends of the measuring line must be deleted. There are several other measurement and visualization tools available in these menus, most of which are self-explanatory, such as overlaying, different drawings of shapes, histogram controls, and viewing controls. It is also possible to apply filters to your images, such as Gaussian, sharpens, and embossing filters. Once you're ready to import your data into another software suite or download it onto a flash drive, it can be accessed in the same directory that you've been working in. It will be in a folder titled Slices Y by default, and you will have simply a stack of TIFF images containing each slice from your dataset. This directory will also include the video fly-through if you chose to download it. It's impossible to cover absolutely everything in a brief pre-recorded training, So it's critical that as you learn CT and gain more experience, you ask the lab managers if you have any questions about the operation of the instrument or in the reconstruction process. Thank you for listening, and good luck with all of your future analysis.